Good morning, guys. We are Andrea, Juliana, Alexis, and me, and today we are going to present you a problem about population growth. First of all, we are going to give you the definition of what is exponential growth. It occurs when the growth rate of the value of a mathematical function is increasing in a proportional way to the function of a value that represent the basic steps to solve a problem. First of all, we had to read the problem, identify the variables, state the model, solve the model, sketch it as a graph, and then get a conclusion. Now I'm going to explain you the exponential growth model. The exponential growth model says we have n times t is equal to n sub 0 times e to the power of r times t. And to explain better, we have that n times t represents the population at time. Then the n sub 0 is the initial size of population. Then the r is the relative rate of growth, and t means time.
The number of bacteria in a culture is modeled by the function n of t equals 500 e to the 0.45 t, where t is measured in years. A. What is the initial population and the relative rate of growth, as a percentage, of this bacterium population? B. How many bacteria are in the culture after 3 hours? C. After how many hours will the number of bacteria reach 10,000? And D. Sketch the graph of the bacterium population function n of t.
Initial population growth of our function is 500. As we said in the last formula, n sub 0 is initial population growth, and the rate of growth is r. In this case, r is 0.45. And to make it as a percentage, we multiply it times 100. How many bacteria are in a culture after 3 hours? First, you need to substitute t for 0.00034. That was gotten from the equivalent in hours of a year. Well, t in this case is 1. It's equivalent to 1 year. So we want it in hours, and we know that 8,760 is equal to 1 year, and we want it in 3 hours. So we multiply t times 1 and divide it by 8,760, and we get 0.00030.
So in order to know after how many hours will the bacteria reach the number of 10,000, we have to replace n of t with 10,000. And then we have to isolate t with the calculator to make the rule of 3.
And we need the rule of 3 to get our result in hours, since the formula has it in years. So we put our 1 year that we know it has 8,760 hours, and since we isolated t, we got a result of 12.7526 years. So we make a rule of 3, and our result is this one. 111,712.776 hours.
I'm going to explain the graph. We can see that t is the independent variable and f of the t is the dependent variable. Then we have the red point, or point A, that expresses the initial population growth, and the blue line that expresses the exponential growth of the bacteria.
You can conclude that exponential functions can also be applied to solve real-life situations, like in this case, where something grows really fast in a short amount of time, like the bacteria in the culture. Another example is heat diffusion.